Bienvenidos, and welcome to this explainer. Let's jump right in. Today, we're breaking down some truly foundational concepts from Lecture 36 by Skip Uni. If you're serious about writing efficient, bulletproof code, mastering static versus dynamic memory allocation in C++ is literally non-negotiable. Over the next few minutes, we're going to completely demystify memory management in C++. We'll unpack the critical differences between stack versus heap memory, see exactly how static memory allocation works under the hood, and contrast it with the total flexibility of dynamic memory allocation. By the end, you'll know exactly what's happening inside your machine when you hit compile. Here is our roadmap for today. We're going to start with a running race analogy, move into static memory and the stack, then dynamic memory and the heap. After that, we'll look at connecting the two, the very real danger of memory leaks, and finally wrap up with deallocating memory manually. Starting with Section 1, the running race analogy, focusing on compile time versus runtime. Okay, let's dive into this. To really wrap our heads around memory allocation, let's use a super relatable running race analogy. Imagine compile time allocation like this. You sign up for a race, and before you even step up to the starting line, you are told exactly how many miles you're running, your time limit, and exactly who you're competing against. Because you know all those details beforehand, that's exactly what compile time allocation is. You're telling the program exactly how much memory it needs before it even executes. But now imagine runtime allocation. You start the race, but you literally only find out how far you need to run while you are already sprinting. In programming, this is dynamic runtime allocation, essentially asking the user for their memory needs while the program is actively running. Moving on to Section 2, static memory and the stack. Safe, automatic, limited. Right out of the gate, by default, standard arrays in C++ use static memory allocation. This static memory lives in a very specific, limited-size location called the stack. Now, the cool thing about the stack is how it handles your functions. When a function executes, an activation record is instantly created inside the stack to store your static variables. And the absolute best part? When that function finishes its job, that activation record is automatically deleted. The memory just cleans itself up without you lifting a finger. Let's look at the specific traits here. When you declare something fixed, like an integer array of size 10, you're explicitly telling the compiler in advance to reserve space for exactly 10 elements. It's permanent. Think of it like buying a specific plot of land. Once it's officially yours, you can't just magically stretch its borders later to make it bigger. It is what it is. Because it's stored in this limited stack memory, and because that activation record is automatically deleted when the function ends, there is absolutely zero risk of a memory leak here. It's incredibly safe. But, a bit rigid. Which brings us to Section 3, dynamic memory and the heap, flexible, massive, manual. So what if you literally don't know the size of your array beforehand? What if you need the total flexibility to create an array of 10, 100, or maybe even 100,000 elements based on user input at runtime? Well, for that, we have to leave the stack and enter the heap. Heap memory is this separate, much larger space used specifically for dynamic allocation. Compared to the tiny constrained stack, the heap is absolutely massive. Now, what's really interesting about this is how you actually claim that heap space. Since the size is dictated at runtime, say a user inputs a variable n, you have to use an extra special keyword, the new keyword. You'd write something like new int n. C++ then carves out an array of whatever size n is right there in that massive heap memory. But here's the catch. You can't just access it directly. You actually need a pointer link to get to it. Let's explore that in Section 4, connecting stack and heap, aka the pointer bridge. We've got a bit of a geographical problem in our architecture here. The function you're running, it's executing inside the tiny stack. But that massive new dynamic array we just made, it's sitting far away in the heap. They are completely separated. So to fix this, we have to literally build a bridge. Step 1, we allocate the dynamic array in the heap using new. Step 2, inside our function over on the stack, we declare a pointer variable. And Step 3, we link them. That pointer in the stack strictly points to the exact memory address of the dynamic array in the heap. Through that bridge, we can access and modify all that heap data right from our stack function. Next up, Section 5, the danger of memory leaks. What exactly happens when that bridge collapses? Okay, I want you to really stop and think about this for a second. We built our pointer bridge, we manipulated our data, and now the function ends. What happens? Remember how stack memory works? The second that function finishes, its activation record in the stack is instantly and automatically destroyed. And guess what lived inside that record? Yep, our pointer bridge. So the crucial point is this. When that pointer is deleted automatically by the stack, the dynamic array you created in the heap using the new keyword survives. C++ does not delete heap memory for you. Without the pointer, your bridge has officially collapsed. You've lost all access to that heap memory forever, yet the data is still sitting there, permanently occupying space. Ladies and gentlemen, that is a memory leak. It's a critical error, and it can crash your programs. Finally, Section 6, Deallocating Memory Manually. Let's talk about cleaning up the heap. Because C++ won't clean up the heap for you, the responsibility falls 100% on your shoulders as the programmer. You have to manually deallocate that memory before the function ends. How? By using the delete keyword. If you dynamically allocated a single normal variable, it's easy. Just write delete PTR. But if you allocated an array, you absolutely must include square brackets and write delete square brackets PTR. Those brackets are vital. They explicitly tell the compiler to go over to the heap and delete the entire array, not just the very first element. And listen, understanding this entire life cycle, from allocating memory in the heap to linking it with a pointer to finally manually deallocating it, is one of the most vital concepts you can master. Interviewers absolutely love this stuff. If you can confidently explain this manual versus automatic cleanup in a technical interview, you're proving you truly understand how C++ interacts with hardware memory. So, we've covered the safety of the stack, the massive flexibility of the heap, the pointer bridge connecting them, and the strict necessity of manual cleanup. Which leaves me with one final question for you to chew on. Is your C++ program leaking memory right now? Seriously, go double-check your code. Did you pair every single new keyword with a delete? It is a fantastic habit to build. Keep practicing, keep coding, and as always, thanks for joining me for this explainer. Catch you next time.